All right, let's go for it. So last time we looked at 3.5 was all about domain. Remember that domain and range, all the good stuff. How do we look at graphs? Now we're going to look at function notation. How do we write stuff down? And quite a bit of stuff to go through. And we were going to cover 3 sections in chapter 3 here, the last 3 sections here. Hopefully you have read them. And real quick here, honesty question, how many read 3.6, 3.7, 3.8 before coming to class today? Ooh, all right, a whole 2 people, 3 people. I think that's the record, right, for this semester, 3 people. All right, so let's go for it. Function notation. Whenever you think about something just being a graph or a relationship between 2 numbers, what we do is we can just say a y. So y is the same thing as 3.5x. And if you remember from last time, from the last section, this was like being paid $7.50 per hour, right? From 0 to 40 hours. Whenever something becomes a function, we can write it a little bit different. And this notation we hardly ever use anymore, but this is the notation you want to get to right here. It's instead of having the y over here, what we do is we say f of x. And by this little f, what we're saying is it's a function of x, which means it fulfills, if you guys remember from last time, that fulfills that function guarantee that if I plug in one single number in for x, I will only get one single number for the output, right? Not 2 different numbers. So this one, a general formula. This one now says it's a function. So it follows the function rule. Alright, with that, let's go for it here. So if f of x is equal to 8x, can you find the following for me? And again, this is probably the easiest, most simplest way that we've found to talk about numbers, as far as a number going in and then a number being as the output. A lot of different notations in the history of mathematics, but this is the one that's sort of stuck. Alright, easy one here. So again, if you're going to plug this in, really this would be 8 times 0. And that's, everybody okay with 0 being the answer? Alright, and again 8 times 5 is 40, so what we're really doing is we're just plugging into this little value there. I'm not writing it down for you because I want you guys to sort of do it in your head. But really, what we're doing is we're doing 8 times whatever number is inside the parenthesis. This guy's called the input. Sometimes the number that's right here. Sometimes it's called the dummy variable because it's whatever is here, that's what you plug in. If it was a triangle, we would plug in a triangle. If it was a star, we would plug in a star. But anybody got an answer for 8 times 10.5? 84. I go with that. Okay, 84. Cool. All right, keep on going here. Let's put it into a little bit of a word problem here. The only thing is, if you did print out the matched problems, right here, instead of a 7, it actually should have been a T. So correct that. Had to be the. All right. So it's for the matched problem. Instead of writing that 7, scratch out the 7, put a little T there because that's the variable. So notice this is S of T. And then T down is that variable right here on the bottom. So when Lorena runs a mile in T minutes, then her average speed in feet per second is given by that right there. So real quick here, let's plug in 8. Get an answer for 8, and then the tough part. Can you explain in one sentence what that means? What do the numbers mean? All right, I'll do it with you. All right. Plug in an 8 for the T value, so it's 88 over 8, which gives us an answer of 11. But in terms of the variable and the formula and all that means, here's what I got here. So running a mile in 8 minutes gives an average speed of 11 feet per second. See if that makes sense there. And again, we're just making sense of the numbers here. So 8, if you go up here, T stood for the how fast that person can run a mile. And the S, the answer, stood for their average speed in feet per second. You guys remember having to do the mile test run, like I think what, 7th grade we had to do it, and then at 10th grade we had to do it again? Anybody beat 11 minutes? 8 minutes? Anybody remember the times from that time? Too long ago, I understand. Okay, so you guys get the next one here. So B, plug in 11 this time, and then can you explain, again I just changed the numbers around just slightly, but can you finish off the problem by yourself? We got it here. Again, just changing numbers around. So 11 is the input now. So 88 divided by 11 actually just gives you an 8 this time. So now this one's a little bit opposite of what we had before here. So running a mile in 11 minutes this time gives an average of 8 feet per second. Are we good there? All right, let's go with something slightly different here. We've got medication, and it says a half-life of 5 days, which means 5 days later there's half of it left in the patient's system here. Again, I'm going to let you guys do this first here. Can you plug in the 5 into the equation, see what you get? Based upon that, tell me what it means here. So hopefully you did this here, plugged in the 5 into this equation here. That made 80 times a half, because 5 over 5 is just a 1, and then we get ourselves a little 40. So what in the world does this mean here? I gotta know what the T means. T is, let's see, 80 nanograms versus millimeter. The patient stops taking it, then T days later the concentration will be this. So T is the number of days, C is the concentration here. So it looks like after 5 days, right, of stop taking the medication, there'll be a concentration of 40, it's called nanograms per milliliter in the person's blood. This is called an exponential equation. We'll get those in chapter 8 as we get those. Here we're just sort of plugging in values here. So C of 10, plug in a 10 over here. 10 divided by 5 is a 2. In this case it's going to be 1/2, and you have to square it first before you do anything else. That makes 80 times 1/4, because a half times a half, and then 80 times a fourth will give you 20. Alright, so the shortcut way of sort of doing it, if you write the units in here, then we all assume that we know what we're talking about. So we don't have to write the English sentence, but just want to make sure that we know what we're talking about as we're right here. So after 10 days, there'll be a concentration of 20 nanograms of medication per milliliter of blood. Okay. And one more. Got to do this here. Some geometry. Some geometry formulas with variables. Got to plug in this whole concept here. So C stands for circumference, usually, right? Circumference, and then look at this. It has this little parentheses, has a little r, so it's circumference based upon a certain radius. Area based upon a certain radius. Alright, so here it is again. It's the naming of it. This is C stands for circumference, R stands for the variable that's been used, because we could use diameter as well, and that would change the formula, right? In this case, it's using R for the radius. Again, naming the formula, A for area, R for the radius. So use the formulas to find the circumference and area of a circular plate if the radius is 5 inches. You guys don't do that? You guys don't walk into like a pizza place and figure out what's the best deal by figuring out the area of the pizza based upon the price? You guys don't do that? You guys are strange. So multiplying the 5 in, it makes 10 pi. And the book, what it normally does, it plugs in approximation 3.14 for pi always when it's trying to find a decimal answer. Then again, if you use a calculator, go for it to finish it off. For some of these problems here, that'll be fine. Some of your calculators do have a pi button on them, so you can just press pi, you're good to go. They may give you slightly different answer though, because this is just an approximation. 3.14, pi is 3.14159, blah blah blah. It goes on forever. Okay, and then always put your units if you can. Whenever you talk about units, plug in the units at the end always. Alright, so a circular plate with the radius of 5 inches, the area of the plate would be pi r squared or pi 5 squared, which makes 25 pi. And again, finishing it off, 25 times 3.14 would get you approximately 78.5. Okay, so we dealt with sort of more like real life situations here. Now let's dive into more of abstract sort of terms here. I give you a formula, you give me the answer, and then at the end something kind of weird will happen. So let's go for it. Here's my formula, f of x. So the function with a variable of x is given as 4x squared minus 3. Can you tell me what is f of 0, f of 3, and then f of negative 2? Should be a little bit easy because you just plug in the formula. So 0 into that gives you 0 squared times 4 minus 3, still just the negative 3. Plug in a 3 this time. Let's see, 3 squared is 9. 9 times 4 is 36, so it'd be 36 subtract 3, or just 33. And a negative 2 plugged in. Gets me negative 2 times negative 2 is 4. 4 times 4 is 16. So how about 16 subtract 3 is 13. Cool, alright. Sometimes you're not just given one formula, you're given two formulas or two functions at the same time. In that case, you do have to label them different. normally we'd say f of x. This is one function. G of x. If we had a third one, normally the label is h of x. But again, just like circumference and area, all of them have different names. So this is different names of your function. So if you say f of 5, that 5 has to be plugged into the f function. If you say g of 5, it has to be plugged into the g function. I'll let you guys some time to do that. Try it yourself. And kind of gets a little weird with e and f, but I'll let you guys try those as well. So alright, those are waiting for me. Let's go for it here. So, are we okay with the 11 for the first one? The 5 has to be plugged in to the f function. That's going to be 10 plus 1. For b, the 5 gets to be plugged into the g function. This time it's going to be, looks like 5 times 5 is 25, subtract 3 or 22. For c, the negative 2 gets plugged into the f function here. For d, negative 2 gets plugged into that, so negative 2 times negative 2 is 4. 4 subtract 3 is a 1. Good so far? And then the weird stuff here. So f of a, that's no fun. That's a variable. That's a variable. So all we got to do is, again, that's why it's called a dummy variable. You just plug in whatever it says. That's what you plug in. And so f of a means I'm going to plug in an a for the x this time. So 2 times a plus 1. If it was a triangle, we would say 2 times triangle plus 1. So g of a gets plugged in. Now that's going to be a squared minus 3 for that one. Alright, formulas, actually functions. Functions don't always have to come as formulas. They could do that, 2x plus 1. They can also come as just individual points. Something like this, where you have f, but it's defined to be an input and an output. Input, output, input, output, and that's it. And so they're just defined as just individual points on a function. So again, the x variable is the one that's the input, the y variable is the output. Alright, and you should find the answer just by looking at it here. So f of negative 4 is the input, the output would be? Yep, it's just the y variable. That's all it is. F of 2, plug that in, answer would be negative 3, I heard, very quietly. Alright, and f of 7, 9, and of course we're going to throw in d over here. Throw in an extra little one here. What is f of 5? The homework does it, I figure I should do it too. Anybody? No? Alright, here we go. Does not exist, right? There's no defined space for 5 here. So there's no defined space for 10 or 17. There's nothing there. So in this case, it does not exist. There's no correlation from 5 to something else. Alright, and another type of problem here. We deal with functions here. This one's going to look kind of weird at first. This is, we call them nested functions, which means you got a function within a function. Or we call it the composition of 2 functions. Kind of weird at first. Let you guys write it down, of course, and then we'll do it together. Alright, so let's talk about at least the meaning of it just real quickly here. So notice this is f, and it's f of g, and it's of 2. So it's nested within each other. So it seems like whatever we get for the g function is going to be sort of our input into the f function. It becomes the variable to plug into the f. So we just kind of go from inside to outside. So we're going to plug in the 2 into the g function. let's do that. So if you plug in a 2 into the g function, what do you get there? Go with 9, is that right? It's going to be 2 times 4 plus 1 makes 9. So g of 2 makes 9. So now what we have is we have f of 9. So the output of the g function became the input into the f function. So now I've got to figure out what in the world is f of 9. Plug into the f function now. It's going to be whatever that is. So let's see, 9 times 9 is 81. 81 times 3. Anybody with that? 243. And the others just waited for me to give the answer. All right. All right, you guys get the next one here. So B is a little different. You get, notice it's the opposite nesting, right? So the 2 goes into the f function first, and whatever the result will be, that number is going to go into the g function. So I'll let you guys try that first by yourself. Alright, hopefully you are done. Let's go for it here. So f of 2 off to the side, that's going to be 2 squared, which is 4. 4 times 3 is 12. So the output here now becomes the input for the g function. So this all stuff became 12. So it's g of 12 this time. And that will be 4 times 12 is 48, plus 1 makes 49. Good there? Just out of curiosity, raise your hands. How many got 49 before I did? Cool, okay. Awesome. Okay, that's 3.6. Jumping to 3.7. And really, actually, yeah, 3.7 is more like a application of functions here. And so we have something called variation. One simple application of functions here. This is how we build a function. One time I was at the snow and saw this guy walking around with this big old glass tube, a plastic tube, but you can sort of see through. And so he came to a portion of the snow and he just started. He plugged in, I mean, it was about the same size as him, and he has this, so he punched it into the snow, and then he started hammering it from the top, just hammering, hammering, and then what he would do is he'd take it out of the snow, and of course, I'm curious, I walk up and say, hey, what are you doing with the snow? And so it was probably a canister about maybe this round, like this, about this tall. And so he was punching into the snow, and then he took it out, and then he had it was a measurement stick basically, and so he looked at how much snow there was, and he said there's really 3 different types of snow. There's one that's very fluffy snow, and he calculated how much of that was fluffy snow. Then he calculated how much there was more like a sort of dense compact snow sort of thing, and then there was more like almost like slushy snow. And based upon that, he was telling me, well, us and about 200 guys, what we do is we go all throughout the Sierra Nevadas over here, and we'll punch the snow. They're called snow tables. And we'll figure out how much, because fluffy snow doesn't have that much water in it, right? The compact snow, that has more water than the fluffy snow, and then the slushy sort of snow has a lot more water. So based upon that, they can calculate how much water is going to flow into the valley by how much snow is in the mountains. I thought that was kind of cool. And they literally calculate pretty precisely. We have not been doing that for the last 3 years, obviously, because there's been no snow in the mountains. But I thought that was interesting. And so then we know how much water is going to go to the farmers. All that is calculated based upon these guys doing this at 200 different locations in the Sierra Nevadas. Pretty slick. Okay, so that's more like a result of something called direct variation. So the more snow you have, that means the more water you're going to have, right, coming into the valley. The less snow you have, so less water in the valley. We good? So direct variation. As one increases, the other increases. As one decreases, the other decreases. Now, This one right here we call direct variation. We call this linear direct variation, which means if one thing goes up, it goes proportionally up. If you think of this one's more like your paycheck. If you get $8 an hour, if you work 1 hour, you get $8. If you work 2 hours, you get $16. Right? It's linear both ways. But it doesn't have to be. Direct variation could also be a square of something. As something increases, the other part increases even faster. Alright, so you can take it to the square, you can take it to the third power, you can take it to whatever power you like. Also, you can have square roots in here too. So it could be proportional to a square root of something. So something goes up but doesn't go up as fast. Now it's going up a little slower than the number. But notice each of these have a little k right over here. K, we call this a proportional constant. We got to figure this out all the time before we do a problem here. So let's do a couple of little problems here just to get us used to this idea. So number 1 says y varies directly with x if y is 24, when x is 8, find y when x is 2. Bless you. And if you print out the match problems, this becomes a lot easier, right? You don't have to write all that stuff down. Okay, so there's always two parts to this. First is to figure out what the k value would be. So let's see, y varies directly with x. Notice it doesn't say y varies directly with the square of x or with the cube of x. It's just x by itself. Cool. So this is a linear proportion here. So y, when it says varies, we're going to put this little equal sign. Directly, so the k always has to be there, and it just says x. It doesn't say the square of x, doesn't say the cube of x, it's just x. So this we call a linear proportion. Then we know some information here. So y is 24 when x is 8. So we got that little situation happening. So notice, first step we're going to do is we're going to just solve for k. Of course, divide by 8, is that right? Anybody got k yet? 3 is good. Okay, so this is the general formula. Now we finally got to the k value. So this is our, we call it proportional constant for this particular problem. So what we do is we write down the problem again, just like we did over here. But now we have one little extra bit of information that we know. We know that k is equal to 3. So find y when x is 2. That's easy now. So let's go for it. And now we know what the k value is. We can figure out the y right away. So notice, writing down the problem, first step really is to find the k value particular to this particular problem. Use it again knowing what the k value is and solve the problem finally for the end. Cool. All right, now let's actually do a real life problem here. Of course, don't need to write all that stuff down first, but I'll just read it to you here. Skydiver jumps from a plane. Like any object that falls towards Earth, the distance the skydiver falls is directly proportional to the square of the time he has been falling until he reaches his terminal velocity. Oh boy, what in the world is that? But I got this one here. It says directly proportional to the square of the time he has been falling. So if the skydiver falls 64 feet in 2 seconds, then how far will he fall in 2.5 seconds? We'll get to there. Alright, since it says directly proportional, here it is. So I put in different variables here. So since it's distance, I'm going to put a D for distance. So then I know my variables, which ones they are here. Equal directly proportional, so I know my k values here somewhere. It says to the square of the time he has been falling. So what do you guys say? To the square of the time he has been falling? Yeah, I'll go with t to the second power. Right, so if you fall from an airplane or you drop a penny or something like that, that penny will go faster and faster and faster, right? Until it reaches terminal velocity. For human beings, falling down to Earth, terminal velocity is 213 miles per hour. That's kind of fast. That's kind of cool. Go that way. All right, so first step, we got to figure out the k value for this particular problem. So if the skydiver falls 64 feet in the first 2 seconds, I got my numbers here. That's cool. Okay, hold on. So that means the distance is going to be 64 feet, and the time, it's going to be 2 seconds to make that happen. What's going to be my k value? Alright, that's going to be a 4k divided by 4, that's going to be 16. Everybody good there? So we're going to plug it back in, knowing what we know now. So d is equal to 16 times t squared. So it took him 2 seconds to fall 64 feet. So how much will that person fall given an extra half second? Plug in 2.5 this time. Ha! Make you guys calculate with a decimal. Love it. Anybody got an answer for this guy? See, 2.5 squared would be a 6.25. And I heard 100. I agree with that. And so how about final answer? You can give me the answer in terms of units as well. And whenever you put the units, that sort of tells me that we know what we're talking about, right? If you put 100 seconds, that means something's wrong because you don't know what we're talking about. Cool. So 100 feet, yes. Which is kind of interesting. So the skydiver fell from the airplane, or jumped from the airplane. Hopefully didn't fall from the airplane. In 2 seconds he went 64 feet, but in this little half a second he went an extra 36 feet. And so he's gaining more and more speed here as he falls. Anybody watch? It was on the NASA channel. I think it was last year, February, I want to say. We had the. It was called the Jump from Space. Did you guys ever see that? If you guys look it up sometime, it's called the Jump from Space. But this guy, he went on a technically a hot air balloon, standing on a platform, going all the way up, and he did reach into space. Part of it was to test the spacesuit that they were looking at. And then he jumps, and it takes him a few seconds before he reaches the atmosphere. And as he's jumping in space, there is no air there, right? So you don't feel like you're falling. You're just, the hot air balloon that you were on, it just becomes smaller and smaller and smaller. But you feel like you're just like, hey, what's happening here? Then all of a sudden you hit into the atmosphere, and like gets all crazy. You just look at it. It's called the Jump from Space, or the other one is the longest sky jump ever, or something like that. First done in the 1960s. And then the record was beaten last year by another fella. All right, keep on going here. This is called direct variation. As something increases, as time increased, so his distance that he fell. But there also something could be inverse variation. Inverse variation just means if something increases, the other one's going to decrease. Or, likewise, if something decreases, the other part's going to increase. For me is driving faster to work, gets me there in a shorter time. Praying that I don't see any police officers, gets me there even shorter. Then going back home, decreasing my speed, it's going to take me a little longer to get home. Cool. Okay, so then that proportion. Okay, so this is called inverse variation. Again, notice what happens here. This little x now is not not multiplying the k value, it's dividing the k value this time. And that's exactly what happens here. There's your direct variation. It's caused by having a division right here. So s varies inversely. Whenever you talk about inversely, you're going to put s is equal to k, and then you're going to divide by whatever that inversely is. In this case, it's the square of t. All right, or x to the fourth, or the cube root of t, whatever you like in there. But it's a division problem this time, whenever you're looking at inverse variation. So let's go for it. Let you guys try this by yourself first. All right, let me start it as well here. So let's see, volume of gas is inversely proportional to the pressure. So first of all, your variables might be a little different than mine, and that's okay. I got, since it's talking about gas, I'm going to put G for gas. G is inversely proportional, so automatically X or K on top and being divided by to the pressure of the gas on the container. So now we're talking about pressure here. So I guess that would be P. Is that right? Does that make sense there? Gas is inversely proportional to the pressure of gas on the container. If the pressure of 48, now this one's a little sneaky here. They put a pressure of 48, not the gas of 48, but a pressure of 48 pounds per square inch corresponds to a volume of 50 cubic feet. So they kind of change the numbers on you here. 48 had to go as the division for the K. Says what pressure is needed to produce a volume of 150 cubic feet. So multiplying this time by 48, and this time, especially with proportional amounts, the proportional, inversely proportional equations here, the K usually is a big number. So we got it. There it is. K is 2400. So now, particular to this canister, there's my formula. All right, see what pressure is needed to produce a volume of 150 cubic feet. Careful there. What's the variable that we're going to be looking for? P is the variable. That means we know what the volume of gas would be, 150. So now we're looking for something that looks like that. Cool. All right. So in this case, probably, let's see, multiply by p both sides. So 150p is equal to 2400, divide by 150. And again, using a calculator if you need to here, or you can chop off the zeros here and see how many times 15 goes into 240. But I got myself 16. Now whenever you talk about pressure, tire pressure, whatever it is, notice it says pounds per square inch right over here. So in this case we're just going to say PSI, and this means pounds per square inch. Again, any kind of tires that we have on a bicycle or a motorcycle or a car, it's always given in this right here. Okay, good there. So we got direct variation, we got inverse variation. Now I get to mix it all up for you in your brain. This is called joint variation. And many times it's not like you just have one variable going to another variable. Many times you have multiple variables. And 2 or 3 different things might be interacting to produce some kind of variation. So the easy one here, y varies jointly with x and z. So you got 2 variables called x and z, and they are contributing to a variation with y. Now some of them could be direct variation, some of them could be inversely. So notice this last one, that's what I want to show you here. This is, I'm trying to think what this is. This has to do with force. Oh, how much force? I almost want to say how much angular momentum you have. This is a formula from physics here. But it says F varies jointly with M1 and M2. This is the mass of 2 objects. Oh, this is a formula for gravity of planets. There you go. And then it says inversely to the square of r. So notice there's direct variation with M1 and M2, but there's an inverse variation with r squared. So those can all be all sort of jumbled together and one little formula. So let's try one. 2 problems here real quick here. So y varies jointly with x and the square of z. Alright, can you set up the formula first? This whole concept of y varies jointly with x and the square of z. After that, can you figure out what the k value would be? And bless you. So let's see, y varies jointly, which means it's going to be a multiplication of k with x, and it's also with the square of z, so it'd be z squared. Alright, I'm going to plug in some stuff here. So if y is 81, hey, that's kind of weird. We know what y is this time. X is 2, and then z is 9. All that put together, I've got to figure what the k value would be. That's going to be, let's see, that's going to be 81 over here. 9 times 9 is 81. 81 times 2 would be 162. Turning that around just so I can see it a little better here. So 81 is equal to 162 times k. Divide both sides by 162. Turns out to be k is equal to 1/2. Is that right? Since 81 is the half of 162. Alright, so now I get to write the formula for this particular problem. Y is equal to 1/2 times x times z to the 2nd power. y is equal to, let's plug all that we need here. We need to find y when x is equal to 4 and then z is equal to 4. That'll work. So in case, the only thing is we have to square the 4. That's going to be 16. 16 times 4, 64. Half of 64 gets me a 32 at the end. Everybody good there? Cool. Okay, so that's just an abstract problem. Let's go on to sort of a real world problem here. Can you guys go from beginning to end with this right here? Let's use the same variable so that at least we have the same stuff on our paper here. So in electricity, the resistance of a cable is directly proportional to its length and inversely proportional to the square of its diameter. Whoa, that's kind of weird. Okay, so I'm going to put R for resistance of a cable is directly proportional to its length. So that means how long it is. That's going to be L times K. Inversely proportional to the square of its diameter. Time if you guys agree here. Inversely means I'm going to be dividing and then the square of its diameter. Alright, and all yours to figure it out. As you do that, I have to tell you a little story, of course. What does all this have to do with anything? Well, the projector cable that we're using right here, this little small one here, this is only thick enough and made enough in order just to transmit a visual image, right? Why did we go from these projector cables down now to an HDMI cable? It was a little bit thicker. It was made a little differently because then an HDMI cable can now send a visual image as well as sound at the same time. We're good? That's the whole performance of an HDMI cable. And so last semester I was experimenting with things like this because I love to experiment with stuff. So they had a 50-foot HDMI cable, which is pretty long for an HDMI cable. And I was trying to see if I can use my laptop on the back of the room. So it takes 50 feet from the projector on top of the classroom all the way to the teacher's desk. So I tacked on another 50 feet going from the teacher's desk to the back of the room. And my only question was, if I flip between PowerPoint slides, will it be flipping on the projector right at the same time? Is there a difference between, or there'll be some resistance to the point that there's a split-second delay? And with 100-foot, 250-foot HDMI cables, there was like a quarter of a second. You could tell that there's a little bit of a lag time there. Kind of cool. Like, dude, there it is. There's your resistance inside a cable. Tacking on another 50 feet, of course, you have to try, right? So you go to the librarian and say, hey, do you have another 50-foot cable of HDMI? Like, sure. Go back through and connect 3 of them together, and then there's some lag time. Yeah, there's about a second lag time at that point. Anyways, it's all about this resistance right here. So what do we got here? We got a resistance is proportional to the length divided by square of the diameter. I have a 100-foot cable, 0.5-inch diameter, and has a resistance of 0.2 ohms. That's kind of cool. So 0.2 ohms, put a 0 in front if you like. Put in whatever you need here. This is 100 feet over here, and it's 0.5, but we're going to square that. And this is more like a typical variation problem. This is probably the way it's more so works out in real life here. Okay, so I got to get rid of this little square right here. So 0.5 times 0.5. Everything else remains the same except that little bottom number becomes 0.25. Good there. Got to get rid of anything that's being squared first, or exponents. Let's multiply both sides by a 0.25, 0.25. So multiplying that out gives you 0.05 is equal to 100k. Divide by 100 on both sides. Voila. Hey, remember what do we do? What do we do when we multiply by divide through by 100? Something about moving the decimal, is that right? You move the decimal to the left, right? Right? Left? Left?
Yes.
Right. Left?
Right.
Right. It's to the left. You got it. So how about this guy for the k value? So 0.0005. And again, this one is particular to this particular cable. Alright, so what will be the resistance of a 300-foot cable made of the same material, and just the diameter has been cut in half here. Alright, let me set up the problem here again. So R is equal to 0.0005 L over D squared. And so the resistance would be 0.0005. That's a 300-foot cable, and it's half as thick. So you got to calculate that for me. And yes, calculator would be sort of handy at this point. Alright, I'm going to go for it. So I got 2.4. Is that what we got? Haha, now the question is, what are the units? What are the units to 2.4? Some weird letters, that's what they are. Okay, they're called ohms. Yeah, I think usually if it's plural there's an S to it, but we'll just leave it as OHM. So not that much more resistance. This was, no, a whole bunch more resistance, right? 10 times more resistance now by increasing the length of the cable 3 times as much, and the diameter, because that decreased. Now you got a whole bunch more issues there with that resistance now, especially if it's a HDMI cable that's 300 feet. Maybe not useful in a classroom sort of thing. Okay, let's jump to 3.8, last section, chapter 3. And this one, most of it's going to be a review of Math 61 stuff, so not as heavy as we've been the last 2 sections here. But this has to do with all the algebra of functions. Whenever you say the algebra of functions, you mean add, subtract, multiply, and divide. But then we have this other little thing here. It's called the composition of functions, or with functions here. So we'll take a look at that as well, what that means. Alright, so this one just sort of shows you just a little something here. Whenever you multiply 2 things here, you can sometimes get a whole new perspective of stuff. So if you know the price of something, you know how price fluctuates based upon how much you have or how much you can sell of something. And if you multiply it times the number that you sold, notice these two functions now. There's called n of x. This is the number that you sold. This is the price that you sold it at. You can get a whole new different situation called revenue. So multiplying two functions can give you a third function which is totally different than the other two functions. This is, you guys will look at that in business later on. And then what you do is you take this revenue function and you subtract it how much it costs you to make something. And if you subtract revenue, subtract cost, this will give you a totally different function called the profit function. So just by subtracting, sometimes by multiplying two functions together, you get a whole new perspective on something, which is kind of cool. The one example that I use is let me see if I have it here. Yeah, I have it here. So here's the definition. We're going to be adding functions, subtracting, multiplying, dividing. Before you start writing that down, this is the example that I like to use here. So let's say one function is the U.S. population. Let's say the G function is the U.S. immigration. Cool. So there's that. So U.S. population is F. G is how much immigration we have, one way or the other. People leaving, people coming. And so what would this give us? If I had to subtract the two functions, I give in the U.S. population and I subtract off the immigration function. Almost there, yeah. It's the U.S. population only in terms of just births and deaths only. Good there? Do you see how that gives us a whole new, different kind of information now, as opposed to just seeing this? So these two, the subtraction of them gave them something totally different perspective. So that's what we want to do. So we have some notation, of course. If you have a parenthesis like this, and then there's two names of functions called g plus or f plus g of x, what you really are saying is you're adding the f function and the g function together. So this is short notation for this, really. If you want to subtract two functions, it's f minus g, and you just write down the variable once. But really what you're doing is you're subtracting the two functions. To multiply, name the two functions, f times g, or fg here, put in parentheses, and have it next to the variable. That means you are multiplying the two functions, and then you can kind of see the division right there. Again, this is inside your textbook here. Let's see what page it's on, just so we have it in front of us. I got, let's see, page 232, is that right? 232 just has the algebra functions: add, subtract, multiply, and divide. Can we do that with functions? Okay, so let's go for it. On the match problems, for some reason, the way they set them up, they have these little, I guess they were using a different program or something, but it kind of looks kind of funny. They have them in these little rectangles for some reason. So again, I just kind of copied and pasted. So here's what we got. We got f function called x squared minus 4. We got a g function called x plus 2. And we want to figure out what in the world is f plus g. So notice it doesn't have a variable in here. Since it does not have a variable, you assume it's a variable of x. So if you just written f plus g, what we assume it's really this right here. It's f plus g in parentheses of x. Alright, in that case, based upon our definition, this means it's the f of x plus the g of x functions. The two functions added together. Again, can you skip a few of these steps? Absolutely. But the f function is x squared minus 4 plus the g function, which is x plus 2. So now really the question is, can you add those up together? Yeah, I guess the x squared, there's no like terms with the x squared, so that stays like that. X, there's no like terms with x, so that's just x. And then negative 4 plus 2, which means minus 2. So I've added that up together. Everybody good there? And again, just putting together like terms. That's all I did. And again, if you can stay ahead of me, go for it. If not, at least keep up with me here. Subtracting the two functions here. So f minus g really just means f minus g of x. I put a little bar line across here so we know which ones we're talking about. So this means f of x subtract g of x this time. And again, going this way here, f of x is x squared minus 4. Now we're subtracting off gx, which is x plus 2. Got to have those parentheses at the end because you're subtracting the whole entire g function. Okay, before we add together like terms, probably easier in this case, kind of like multiply this little negative 1 into here and here, if you like. Kind of do that. You can just drop the parentheses, that's fine too. So let's drop the parentheses. You're going to multiply this times a negative times a x makes minus x. Negative times a 2 makes minus 2. And anybody with an answer yet? Cool, I'll go with that here. X squared minus x. In this case, it's going to be minus 6. Right, your job is C and D. Can you multiply the two functions together? F times g. Can you divide the two functions? Let you guys try that first though. Alright, going on to multiplication here. So f times g. That means f of x times g of x, and we're going to do something called FOIL method. Is that right? Because you got a binomial times another binomial. So hopefully we are foiling the first two terms. X squared times x is x cubed. Outside terms makes now positive 2x squared. Inside terms gives you minus 4x, and the last term gives you a minus 8. Any like terms to put together? Nah, so there's the answer there. Division. Okay, so f over g means f divided by g of x, or really the f function on top, the g function on the bottom, and the f function is x squared minus 4. G function is x plus 2. And the only thing we've got to do here is maybe, possibly, just maybe, things cancel. Okay. How about x squared minus 4? Does that factor? It sure does, doesn't it? Doesn't that factor into x plus 2x minus 2? X plus 2 on the bottom, so voila. X plus 2's will cancel themselves out, leaving us with x minus 2 as our final answer. If they don't cancel each other out, we just leave it as that. We would just leave it as x squared minus 4 over x plus 2. But if they do cancel, we have to write them in lowest terms, just like any fraction. We always have to write in lowest terms. Alright, a little bit more complicated. I'll let you guys try these yourself here. So how about if we had three functions? We have f of x here, this is g of x over here, and we have h of x over here. So I'll give you guys a few minutes here, see if you guys can put those together depending on which functions you need to add, multiply, subtract, divide, whatever, which one it says to do with, but give you guys a few minutes to try this yourself. Alright, let me give you maybe the answers one by one. So for A, adding f and g together should give us an answer of 3x squared minus 7x minus 6. Alright, for B, multiplying the f and the h together, so we really have 3x plus 2 times x minus 4, and multiplying that out, again foiling it out. Adding like terms together should give you 3x squared minus 10x minus 8. Alright, and C, being the long one, it's f times g, 3x plus 2 times that little trinomial right at the end there. So this is the not so fun one here, 9x cubed, then we got a minus 30x squared minus 24x. Little trick that I usually do if I'm multiplying a binomial with a trinomial, because I know there'll be like terms, instead of writing it horizontally and keep on sort of writing it all this way, what I like to do is I multiply through here and I just put it underneath its like term. So 6x squared, this will give you a minus 20x minus 16, and then when I can add it together I already have all my like terms in a row, so it kind of helps out with the minus 24x squared minus 44x minus 16 at the end there. Alright, and last one, D. It's the division between g and f. And still this is just a variable x, so the g function goes on top, the f function goes on the bottom. And we have the trinomial goes on top, the binomial on the bottom, and the only question is, does that trinomial factor? Maybe. I see a few yeses in the audience. Okay. Yep, that does factor into 3x. Well, let's do it together here. So 3x squared, the only way I can do that is a 3x times x. That's only one choice here. With the minus 8 at the end, it could be 8 and 1 or 4 and a 2. Probably more leaning towards the 4 and the 2. Maybe a positive 2 here, especially if these two are going to reduce. Minus 4 over here. Let's just check. This is a negative 12x plus 2x, and that's perfect. That will give you a negative 10x in the middle. Therefore, that's the correct factored form, and therefore the 3x plus 2 cancel to give us x minus 4 is our final answer. Okay, so we've been dealing with formulas, or we've been dealing with functions as a whole. Sometimes we actually don't have to deal with the whole entire function. Sometimes we actually just want an individual point from that function. So this is what this is about right here. So notice on A over here, it's no longer f plus g of x, it's actually f plus g of 3. So again, don't want the whole entire function, I just want the individual point right at that value, and that's it. So this will probably work a little bit different. And really this is more about why work more than you have to. Because we could get f plus g of x, get that function, then plug in 3. But there's no point to do so if I can just do this. I can split them off into two different pieces, f of 3 plus g of 3. And the only thing for me to find out, what in the world is f of 3? If I plug in a 3 in here, what would I get? You get a 9, huh? 3 times 4 is 12. 12 subtract 3 is a 9, so 9 for f of 3. Oh boy, then I gotta get g of 3. That one we may have to do on the side here. So how about on the side here, I get an 18. But you guys try it on the side, just to make sure I'm correct, please. Nick, a question? Go ahead.
I'm just lost.
Sure. Let me go back here. Got a question about the 9 or the f of 3? Where's the question, or the whole thing?
The 9 and 18
Oh, okay, got it. So, everybody okay with this 3 being my variable now, right? So it comes in, but my variable is actually a certain point, so this is really f of 3. I gotta take this 3, I'm gonna plug it into this f function right here. So 3 goes in for this x right here. 3 times 4 is 12. 12 subtract 3 gets me that little 9 right over here. So I'm really just plugging into this formula right here. G of 3, you guys have to plug into this right here, G of 3. You verify with me just to make sure, is that truly an 18 or not, or I was just doing this too fast in my head. So plug in the 3 into that. That's 36 over here, right? 36 minus 21. I don't know. Okay, I see one person saying yes. Want to get a second on that just real quick here. So that 3 goes into this function right here. You have to do it off to the side somewhere. So put g of 3, 4 times 3 squared minus 7 times 3 plus 3. Are we good? Is that an 18? Okay, cool. I got a few people saying 18. I agree there. Just in case, here it is. I plugged in the 3 into the g function. So that's going to be 9. 9 times 4 is 36, minus 21 plus 3. So that means it'll be a 15 plus 3, or 18. Are we good there? So notice instead of building the function called f plus g of x, we just take individual points in there. Makes it a lot easier. Okay, so for b, how about f of -1 times h of -1, whatever that's going to be. So plug in the -1. Alright, so f of -1, if I plug into that, gives me -4. How about a -7 or -7? A -1 plugged into h, what do you guys get there? -2. Cool, so the answer result would be, how about a 14 for b, as you plug in the values. Alright, f times g of 0, so how about a 0 in for the f, a 0 in for the g. That should be a little easier one there. In for f, 0 times 4 is 0, subtract 3 gets you a -3. 0 in for the g function gives you a +3 because it's the number right at the end, and how about a -9 at the end? Alright, and this one, so g of 10 on top, g of f of 10 on the bottom and give you guys a little bit of time to try that one yourself. Alright, I'm going to give the answer here. So I think we should get 333 on top. And plug in a 10 for the f gets you 40 subtract 3 is a 37. And as you start dividing 37 into 333, you get yourself a 9 when you do that. Just got to do a little bit of long division. Okay, so this is the algebra of functions. We get to add, subtract, multiply, divide. Sometimes it's the whole entire function, sometimes it's just an individual point or a value at a function. And the other part is the composition of functions. Something that we can do that we can't do with numbers is we could stuff one function into another function. And so this is the composition of functions. Has this, it's kind of funny, it's not a closed dot. Closed dot would mean a multiplication. It's kind of like this little open dot. And again, we're just running out of different symbols to use, that's all. So we have open dots, we have closed dots. Okay, so what does this really mean? And again, we're on, let me just check what page number. If you want to follow along in the book here, we're on page 234. So here's the notation for it. It's f of g of x, and we actually have already done this. We did it with individual points, but now we're going to do it with the whole entire function. And it just says this x goes into the g function. Whatever comes out of this one, that input or the output of the g function becomes the input into the f function. Heard that before today? I think we talked about that, right? With different numbers though, right? And so x becomes g of x, and then g of x goes into f. Okay. Looks kind of weird at first. Let me give you maybe an example just real quickly here, because this is somewhat new here. Let's say the f function is x plus 5. So the f function, what it does is adds 5 to whatever number you have. Alright, let's say the g function is x plus 7. G function just adds 7 to whatever number you have. And again, I figure this would be a better, because the book really doesn't explain this here. This is what we want to do. I want to put in these two functions together. Let's just say I'm going to use the number 2. I think we've done this before, didn't we? So let's take this 2 here. Let's take this 2, let's plug it into the g function. What do we get as the output? We get 9, right? Because it's 2 plus 7 is 9. We're going to take that 9, we're going to plug it into the f function. 9 plus 5 is 14. Are we good? So notice what happens. This composition of functions, what it does, it's done both of the procedures at once. It's added the 5 and the 7 to the 2 to make 14. What we want to do is we want to do that for the function as a whole. We want to put these two functions together as one single function. And so let's see what's going to happen here. The equation for the g of x, notice this is g of x now, not g of 2. This is g of x. G of x, the formula is x plus 7. Good there? We're going to take this x plus 7 and we're going to plug it in to this little x right here. So see how this works here. Again, the f function is x plus 5. The input is x plus 7, so it's going to look like this. It's going to go, we're going to plug in x plus 7 for this guy. So how about x plus 7 plus 5? Good there? There's my variable that used to be x for my f function. And as I simplify it, notice what I get. I get x plus 12. And notice real quickly here, if I put a 2 into here, right, wouldn't that be 14 as well? But notice what I've done though. I've put these two functions together, so I only have to do one single process to figure out the answer. So The g function said I got to add 7 to it. The f function says I got to add 5 to it. If I combine the processes together, I can have one individual function that says I just need to add 12. I'll always get the same answer each time. Okay, good there? Where's this used at? The way I've seen it used at is in like in retail. You know how you have like discounts? Like you get an instant 10% off, then you have a 20% sale on something. And so instead of doing those 3 processes, like whatever the sale price is, you take 10% off, you take a 20% off the sale, and then you get a discount, let's say $20. What happens is, especially like in humongous, like Walmart or something, what they'll do is they'll send a function that does all those processes as just one function, because you can just sort of calculate faster, that's all. So it'll take the 10% off, take the 20% off for the sale, and take the $20 off all at once. So it's just a little faster process for the calculator. Okay, so let's go for it here. Let's try just 2 of these, just real quickly here. We'll technically come back to this in chapter 8, and we're going to talk about exponential and logarithmic functions here. Okay, but just to get the algebra sense of it. So f of x is x minus 4. G of x is x squared plus 3x. A little bit more complicated than was the example. So we want the composition of f and g. Okay, the short way of writing it is f of g of x. Of course, the honesty question comes up. Raise your hand if you say, Mr. H, now I wish I would have read ahead. I wish I would have read 3.7, 3.8. Okay, got 4 honest people here. Okay. Okay, the g function is x squared plus 3x. We're going to plug this guy into the f function. Good there. There's my new variable. There's my new variable. It's going to come into this function here. So this x now is going to be changed into x squared plus 3x. So here it goes. X squared plus 3x. And then we got subtract 4, because that's what the f function does. It subtracts 4 from whatever you have. Alright, in this case, voila. I just got to drop the parentheses here. That's all we need to do here, and we're done. That was an easy one. Cool. Alright, and then the other way. So this one we're going to do g of f of x, and these guys are different from each other. So we're going to plug in the f function into the g function. Okay, the f function is subtracting off 4, so x minus 4. Okay, so let's take this guy and we're going to plug it into, ooh, this is going to be weird. We're going to plug into x squared. We're going to square this and then add 3 times that. So this case is going to be x minus 4 being squared. So notice the exact same thing as g of x is. Plus 3 times the x, or x minus 4. Okay, everybody okay with just putting in the variables there? Okay, I got to do some work here. Got a x minus 4 times itself. Got to FOIL that out. X minus 4 times another x minus 4, FOIL it out. Or remember the little quick method. Whenever you are squaring a binomial, you square the first term, put the same sign, and you do x times 4, 4x, and double it to make 8x. Then you take the minus 4, you square it. Negative 4 times negative 4 is a positive 16. So square, double the middle, or double the product, square the end. Distribute the 3 here, 3 to the x, 3 to the negative 4. And then finally adding like terms together. I'll let you guys finish it off. Cool. All right, finish. Final answer. How about x squared minus 5x plus 4? So before we leave chapter 3 here, got to show you the little jump from space here. It's just a 1-minute video. Get the volume up here.
Facing that big tower. Anybody can hear? I'm facing that big tower.
Okay, the wind's out of the east. So get the out of the east.
Oh, you're feeling we're coming your way, bud. Carry on, I need clear.
Release.
If you stay here, just stay right if you feel ashamed. Yeah, we all feel the same.
Feel like time is out of the east. The wind is out of the east.
On the parachute, we have quite a bit of control. By putting this
Wind's out of the east, Felix. Wind's out of the
by
east.
putting the cords, we can control a fair amount of control on this path into this landing. Well, we see that smoke right below.
Speed 75. Showing Felix at a stable.
It's 5,000 feet now, so we're on the altitude out there. I'm not sure the altitude on the ground.
Felix is back on something to do. The record holder.
The longer video has like his altitude and all that stuff where he's at. I think it was. I don't know. I already forgot how many feet up high he was in the air and stuff. And he fell in space itself. He fell for like 6 minutes or something like that. It was actually pretty cool. All right.